Hello everyone, and welcome to a video on trigonometric integrals for a typical Calc 2 course. And what I did in a previous video is sort of review some of the trig identities that we will use, and we took a look at some of the potential trig integrals that you will see in Calc 2, but that you also might have seen in Calc 1. For example, remembering we can't integrate tangent squared x without that rewrite of secant squared x minus 1. Using that Pythagorean identity and so forth. So if you're just now tuning in, you may want to watch that video to get started with trig integrals before watching this one. So let's assume that we are ready to go, and we have an integral of cosine cubed of 4x dx. So we are integrating with respect to x, and one might think, oh, I can use substitution this. Well, let's try it. If u equals cosine of 4x, I could easily rewrite that as u cubed. That's not a problem for my integrand. What is the problem is that my derivative of u, cosine 4x, would be negative 4 sine of 4x dx. And see, I don't have a sine of 4x function in there. So if we only have one trig function, I need to separate this out so that I can make sure whatever I have as my u, I also have that function in my du. So let's see how else we can talk about this. Well, I do know that cosine cubed of 4x is the same thing as cosine squared of 4x times cosine of 4x dx. All I have done is a rewrite. Just sort of using that idea that, if you're cubing something, it could be rewritten as the square times the linear. Sure. Well, how does that help me? I'm still not ready for a u substitution. That is kind of where I'm headed, but I'm not ready for it yet. You're still all in terms of cosine. Can I write one of these functions in terms of sine instead of in terms of cosine? Ooh, I sure can. I can rewrite cosine squared of 4x as the quantity 1 minus sine squared of 4x using that Pythagorean identity, right? Because we should know and be able to use at any time cosine squared of an angle plus sine squared of an angle is 1. So these Pythagoreans are going to get used often. So maybe a good idea when you start this homework is to write down the 3 Pythagorean identities. This one, the one that uses tangent squared and secant squared, and then the one with cotangent squared and cosecant squared, as well as maybe my 6 trig derivatives. Okay, so now I'm actually ready for a u substitution. It looks a lot more complicated than it did in the beginning, right? It was just cosine cubed. I understand. But now look and see if u is sine of 4x. Let's just look at what that part looks like. Well, this could be written as 1 minus u squared. Okay, now how about the rest? Well, if u is sine of 4x, du is 4 cosine 4x dx. And look, I can easily manipulate or multiply in a 4 if I multiply out a 1/4. And now I can see I have my entire du right here. So I will put a 1/4 in front of my antiderivative, and the rest of this just became du. And my integral should be pretty simple to integrate. Mostly we're setting these up so we can use basic power rule. So this is going to be 1/4. I'll just keep that 1/4 on the outside. Antiderivative of 1 with respect to u becomes u, and then antiderivative of u squared becomes u cubed over 3. Don't forget your plus c, and lastly, don't forget to put back in your u, and my u in this case was sine of 4x. So even though my problem didn't actually start with sines, I'm ending with sines. Right? My problem started as cosine cubed. So here's the main idea of these. You have to make sure that whatever you assign to be your u, the rest of the integral has to be able to be turned into u's And make sure you preserve your du. This du is a big deal, right? We need that function. So for example, when I take the derivative of tangent, I'm going to make sure that I'm reserving secant squared because that will be my du. So let's just stick with sine and cosine for a few more here. And let's go through this one and see why this one might be a little bit different. Well, this one I do have sine and cosine, which is great. Now, either one, theoretically right now, you might think could be my u. But let's take a look at why our u would be pretty difficult if it was sine of theta. So just watch for a second. I would not recommend writing this part down. Just watch so you can see when you know you've picked the wrong function for u. If I let u be sine of theta, I could easily rewrite that as u to the fifth. Okay, fantastic. But du is cosine theta d theta in that case. And again, I can easily think of this as cosine theta times cosine theta d theta, right? Because that's what cosine squared theta is. But only one of these cosines is going to be used for the du. Right? Only one of them. So I'm still going to have a du, but I still have a cosine of theta here that's not necessarily easy to write in terms of u. If I do that, I'm going to have to change my angle. I don't want to do that. So that tells you, hey, maybe u shouldn't be sine of theta. Okay, let's try the other way. Now here we're going to see this go really well. So what happens if I let u be cosine of theta? We recognize that du should be negative sine theta d theta. Okay. Well, I can rewrite this. That way I reserve my du, so I'm going to throw a negative inside my integrand and a negative outside. I'm going to write 1 sine of theta because that's what I need for my du. At the very end, I'll put d theta. I don't like putting d theta in the middle. Then how many sines would be left? Well, if I, factor out 1 sine, I have sine to the 4th of theta and a cosine squared of theta. So whether you write this down or just kind of think about it, this piece right here that I'm underlining in the red is going to become my du. So I'll kind of highlight it as well. That is going to be du, so that's going to be used. This is going to be in green u squared. Okay. The trick now is, can I write sine to the 4th in terms of cosine? So let's think back. I'm going to do a little bit of side work here. Cosine squared theta plus sine squared theta is 1. And I'm trying to solve for sine to the 4th. So let's just first solve for sine squared theta. We'll subtract cosine squared theta from both sides. And if you want to turn this into sine to the 4th, I have to square the left-hand side. And this is where you need to remember your algebra, which means I square the right-hand side. Squaring is a function. You're doing it once to the left and once to the right to remain equal or balanced. So now this is sine to the 4th of theta, and this side is 1 minus cosine squared theta quantity squared. I don't necessarily square that out, or distribute that all out. Now I'm just going to put it in over here. So negative on the outside. The rest of that red is going to be du. The sine to the 4th is 1 minus cosine squared theta. We'll go back to your u. What is that in terms of u? Cosine squared theta would be u squared. And then that green cosine squared theta is u squared. Okay, so I will now distribute this out. 1 minus 2u squared plus u to the 4th times u squared And I will distribute in that u squared, 2u to the fourth. When you are multiplying with the same base, you add your exponents, so be very careful with your exponent rules. And now I'm just integrating using power rule. A negative is on the outside. You can distribute it if you so choose. U cubed over 3, 2u to the fifth over 5, and u to the seventh over 7. I will put my u back in. U was cosine theta. Cosine cubed theta over 3 minus 2 cosine to the fifth theta over 5, and plus cosine to the seventh theta over 7 plus c. And again, some systems, when you're typing in cosine squared theta, they understand what that means, but maybe not for cosine to the fifth. So you might have to type in things like cosine of your angle raised to the fifth, like so. So again, if you have an even number, so sine to the fourth, sine to the sixth, sine to the eighth, etc., of your angle, and of course your angles match, then you can use your Pythagorean identity to rewrite that in terms of your function that you want. So if I'm talking about sine and cosine, I can rewrite them in terms of each other to any even power. It's the odd powers that give us a little bit tricky if you're using the Pythagorean identity. Okay, so let's look at a different one. All right, so sine squared theta, cosine squared theta, d theta. And I want you to look, kind of zoom out. So they did a study of, mathematicians' brains, how they work, and the reason that you're able to be good at problems like this, or once you feel confident about problems like this, is because you have that ability to zoom out and look big picture, and then when you need to zoom in and focus on detail, and then step back and zoom out and look at what you have. Identify if you think you're on the right path, or what are you trying to do big picture wise. So it's that zoom in, zoom out idea that's going to make you successful in these problems. So I'm going to zoom back out for a second and say, okay, well, let me just think long term here. Sine and cosine are obviously related. I like the fact that they're both in my integrand, but if u is sine theta, I just chose it because it came first, then du is just one of those cosine theta d thetas. Now plan ahead. You can write your u to any power, so I'm no longer looking at that piece because I can write u to any power. But if I need one of these cosines for my du, that's only going to leave one cosine of theta behind, and that's going to be tricky to write in terms of u without changing the angle. Okay, so if I zoom back out and think, okay, sine isn't going to work for u, well, the same reason cosine is not going to work for u. Because if u is cosine, again, you can write u to any power. I'm no longer looking at that piece, but the same thing occurs here. This is one sine of theta, one sine of theta as a product. So du being negative sine theta d theta, I'm only going to use one of these, and I'm going to have a leftover. And I can't easily write that in terms of my u. So again, that one is not going to be, what I'll say easy to work with. So what are our other choices? Well, I hope that you remember we, in the last video, worked with this double angle formula for cosine, and we said that there were a couple different identities that we worked with. One of them was 2 cosine squared theta minus 1. And if you solved this identity for the cosine squared theta, I would add 1 and then divide by 2, so it looked something like so. And all it's doing, it is not a new identity. It was taking the double angle identity that we knew previously and just solving it for, instead of the double angle, solving it for the squared. Okay, So this is what I call the reduction formula because it's going to reduce the power. So this is used when you don't want to integrate or don't want to work with cosine squared theta. You would rather work with a linear statement because I can actually integrate cosine of 2 theta all day long. Okay, so sine squared theta is almost the exact same formula, and I again showed that in the previous video, but that one has a minus because it still comes from the cosine of 2 theta formula. So I'm saying these are equivalent. I am just doing a rewrite. Sine squared of theta is equal to that right there, 1/2 times the quantity 1 minus cosine 2 theta, reduction formula. And then cosine squared theta is also 1/2 1 plus cosine 2 theta d theta. Again, this is just a rewrite. I am not nearly ready to integrate yet. So 1/2 times 1/2 is 1/4. I am going to pull out the coefficient in front. Just be careful in the end that you don't forget about that coefficient. And then when I multiply 1 minus cosine of 2 theta as a quantity times the quantity 1 plus cosine 2 theta, they are the difference of squares. So they multiply to be, excuse me, they are conjugates. So they multiply to be the difference of squares. So I get 1 minus cosine squared of 2 theta. Well, I know what that is. 1 minus cosine squared is sine squared. This is what makes trig, I think, fun to work with, is because it's manipulable. So you have options or choices and kind of some techniques that we can work with to make these problems look and feel workable. Well, I kind of am at the same place I was when I started, but now I don't even have a cosine squared with it. But the same principle is going to occur that I don't really have a good u du pairing in here. So I'm going to use the reduction formula again. So I have this 1/4 out front. The reduction formula is 1/2 1 minus cosine, and it's a double angle. So if my angle was 2 theta, now it's 4 theta. It's a double angle formula. That's what it's coming from. So I'll do a rewrite, and I think I'll be ready to integrate here pretty soon. 1 minus cosine 4 theta, all with respect to theta. And some people like brackets, you know, because they like to alternate parentheses and brackets. It's up to you. I'm ready to integrate because I can integrate this. So this is 1/8. I'll just leave that in the front because I'm not doing anything necessarily with this. Antiderivative of 1 with respect to theta becomes theta. And then the antiderivative of this minus cosine 4 theta is going to become minus sine of 4 theta over 4. Hopefully you've seen that enough now, plus c. I didn't even need a u substitution, which is kind of nice because then I'm just done. So you probably haven't worked with that reduction formula in the past. Okay, 2 more quick problems here. This number 6 is asking us to deal with a sine squared of x function, and it's paired with a cotangent cubed of x. So let's just go off to the side for a minute and think about our Pythagorean identities. So we have 3 of them. We have already worked with sine squared of an angle plus cosine squared of an angle is 1. That comes from our basic right triangle trigonometry and Pythagorean theorem. We can take that basic Pythagorean identity and divide through by, let's say, sine squared of theta every single term. So sine squared over sine squared is 1 as a function. Cosine squared theta over sine squared theta would be cotangent squared of theta. And 1 over sine squared theta, or the reciprocal of sine squared theta, is cosecant squared theta. So I know some of you may have memorized those as if, you know, it's a different or new or unique identity, but really it just comes from the basic Pythagorean identity. Sine squared theta plus cosine squared theta is 1. I will do the same thing one more time here and divide each term by cosine squared of theta. So sine squared theta divided by cosine squared theta, starting back from the beginning, would be tangent squared of my angle, plus cosine squared theta over cosine squared theta is 1. Then the reciprocal of cosine squared theta is secant squared theta. And this tells us a lot, actually. So when you're dealing with sines, you kind of want to have cosines, right? When we're dealing with cotangents, I really like cosecants. And further, when I have tangents, I really like them to be with secants. Now, not only are their Pythagoreans each other, but their derivatives are each other as well. So that's going to become really helpful. So as I look back at number 6, I kind of have two choices. I can rewrite this entire integrand in terms of cotangents and cosecants, or I can go to sines and cosines. Of course, you can go to tangents and secants, but considering I don't have either one, let's not make it harder than we have to. So most students prefer to go to good old trusty sine and cosine. So I'm going to leave sine squared x as my first factor here in this integrand. And I'm going to rewrite cotangent cubed x as cosine cubed x over sine cubed x. And here's sometimes where your pencil might even be writing faster than what you can do. We do see that some of these factors divide to 1, meaning sine squared over sine squared is 1, and that would just leave cosine cubed x over 1 factor of sine x dx. Okay, now don't write this down, but just look for a second at one potential sort of pitfall or problem that I don't want you to run into. If you're not careful with who is your u, and you just say, okay, well, I first see cosine, so I'm going to let u equal cosine of x. Well, let's just take a look at why this will not work. Because I think it's my job in these videos not just to tell you how to do the problem successfully, but also to help you maybe mitigate some of your errors or lessen your chance for frustration and really help you find some mistakes if you've made them. So if u is cosine x, du is negative sine x dx. Here's the problem. It looks fine because you can write u cubed, right? That looks okay. What's not fine is this denominator. Your du is not in a denominator. It would be in that numerator, and it's not. So that does not organically match, so that is not going to be the way that we go. So instead, we're going to say let u equal that denominator, because again, I can always write something over u and then calculate from there. So if u is sine of x, du will be cosine of x dx. Okay, well, I'm going to reserve one of my du's. So here's the cosine x dx, right? That will be my du. And then I'll write what I have left. Well, that's going to leave in my numerator cosine squared x, right? Because cosine times cosine squared would have made that cosine cubed. And I'm just right now writing out this equivalence. I have done no u substitution. I'm just getting ready to do my u substitution. All right, well, if u is sine x, I have to be able to write everything in my integrand in terms of u and du. All right, I kind of can do it with most of it, but this cosine squared x, can you write that in terms of your u? Well, sure, because we know sine squared x plus cosine squared x is 1. I know, and I'll do one quick rewrite here just so you can see it, that cosine squared x could be rewritten using that Pythagorean identity as 1 minus sine squared x. Now, don't get too crazy with just crossing things out, and students like to use the word cancel. I'm not going to cancel anything. I'm either going to add two terms to 0, or I'm going to divide them to be a 1. So for example, those have nothing in common because I'm adding and subtracting and multiplying across that numerator. I'm not just dividing those two factors. So I'm going to keep going down the path that I was going and turn everything into u's and du's. And like we said before, that cosine of x dx is what becomes my du. The 1 minus sine squared x, well, that's going to become, look at your u, that's going to become 1 minus u squared, and this is all over u. So I've at least turned my integrand in terms of u's and du's, so I think I'm ready to maybe separate and reduce so I can see this a little bit more. And what I mean by that is everything in my integrand is being divided by u. So if I write it as such, 1 over u minus u squared over u, maybe you can see this just a little bit easier. So this antiderivative is the same thing as 1 over u minus u. It's all with respect to u. So hopefully you remember how to antidifferentiate 1 over u. That was our natural log of u. Don't forget your absolute value bars, otherwise you're not equivalent. Minus u squared over 2 plus c. So now I just have to put my u back in. U was sine of x, so I will put that back in. Natural log absolute value bars, sine x minus sine squared x over 2 plus c. Okay, not too terrible. Again, you're going to spend quite a bit of time just identifying who is your u, who is your du, and then just rewriting that integrand accordingly. All right, one last one with sines and cosines. Again, let's kind of think zoom out here for a second, and let's really take a look at what we're doing. And we have a binomial, a minus b, for example, quantity squared. So nothing says that I just can't square this out. And if you need to see it as the factor times itself, you can. Doesn't hurt. And then I'll multiply this out. So I do get x squared minus 2x cosine of 3x, and then plus cosine squared of that 3x. And so I really have 3 completely separate antiderivatives that I have to do. I have to antidifferentiate x squared, because I'm going to go term by term here. That I can do by power rule. I have to integrate my second or middle term, which is 2x cosine 3x, which we actually have a new Calc 2 antiderivative technique. Remember by parts? And then I have cosine squared of 3x, and that's going to be that reduction formula that we've worked with already in this video. So I'm going to go ahead and integrate each term here as we go. So this one will become x cubed over 3. I'll put my plus c at the end. And I'm going to write this out just so it's a little bit more clear here. I'm going to take the antiderivative of this second term with respect to x and the antiderivative of my yellow or third term here with respect to x so that I can see this individually. All right, so we said that second one was by parts, so that's exactly what I'm going to do. So I'm going to say u equals and dv equals. I'm just going to do a standard by parts. You are certainly welcome to do tabular if you are familiar with that. So if u is the algebraic piece, or the piece that's going to break down to 0 if you do the derivative enough time, dv then should be the rest of that integrand, so it's cosine 3x dx. Well, then if I have u, I need to find du, so derivative of negative 2x would be negative 2 dx. And the antiderivative of cosine of 3x with respect to x would be 1/3 sine of 3x, because remember, you have to divide when you're doing that antiderivative. Okay, so then this becomes uv, and the reason I put this -2 factor in is because now I don't have to worry about trying to distribute a negative later, and I don't have to worry about trying to remember a 2 or anything later. It's just all already built into the problem. The only thing I kind of am worried about losing here is this x cubed over 3, because that piece was integrated a long time ago. Okay, so I'll keep writing that down, and then I have u times v. So this will become minus, so I'll change this here to be minus 2x over 3 sine 3x. And then it's minus the antiderivative of v, and I'm just going to write this down, du. Okay? And then I will integrate the last term here in a minute. I'm just going to continue with this one for a second here. So this is going to become plus, because you have a -2 times the negative, and there's going to be a 2/3 as a coefficient of sine 3x dx. And I do know how to integrate that piece. This will be a cosine of 3x. I will have to divide by another 3, so that'll make this a plus 2/9, and it's going to have to be negative. So I'm going to change this back to minus 2/9. And I'll copy the first two terms that I have already integrated. Here I am. So far, I am not done. I still have to integrate cosine squared of 3x. Well, that's that reduction formula. And this reduction formula, again, comes from that double angle formula. So I know this is equivalent to 1/2 1 plus the cosine of, and it's a double angle. So if my angle was 3x, now my angle is 6x. And the reason I separated this into all three terms is because then you can factor that 1/2 out in front of that integral, because the 1/2 does go to the entire reduction formula. But if you write it and keep it all in one integrand like it was in the beginning, I can't pull that 1/2 out front of every term. So I like to integrate this just term by term, one at a time. So if I integrate a 1, because I won't forget this half, so I've got this half out front here. So the 1 will become x, and the cosine of 6x is going to become a sine of 6x divided by 6. And if you want to distribute in this half, you can. It would just be x over 2 and sine of 6x over 12. That is entirely up to you. So this had three kind of different techniques, and besides the by parts, didn't really use a u substitution. It just used that by parts formula or by parts integration. So kind of interesting to look at in molding some of our trig techniques with some of the previously learned techniques like by parts. So this is only part of what we're going to learn for trig integrals. I will make other videos here in a minute on trig integrals that use functions other than sine and cosine, so look for that to help you as well. Thanks for watching. Hope you found it helpful.